And we're live in 5,
4, 3,
2,
1.
All right. Well, good morning, everyone. This is Amir Abdul-Jabbar here with the Swedish Neuroscience Institute. I hope you all can hear us well. We have the honor of having the team over at Houston Methodist with us, our former fellow Yevgeniy Freyvert. Yev, great to see you. Running the Journal Club today. And yeah, we'll jump right into it and go ahead and introduce your team of fellows and residents. I know you've got a great team out there. And we really appreciate you kind of taking the lead with this month's Journal Club.
Yeah, fantastic. Thank you. Thanks for having us. Let me just share my screen here. All right. Yeah, this is a very timely topic. It's kind of the hot new thing in spine surgery and pretty much across the board in many surgical specialties. So the objectives for today, we'll discuss artificial intelligence in spine surgery. I'll start off with introduction and some definitions. Then we'll do a presentation of the literature with our team, and then we'll leave a little bit of time for questions and discussion. So first off, as I mentioned, this is a very timely topic, and if you look at Google Trends, both in terms of web searches and news searches, right now we're kind of at the peak. The last year or two have definitely been very popular in terms of artificial intelligence, and this is also true for the scientific literature. As we know, artificial intelligence is pretty broadly applicable in spine surgery across the board. If you take a look at the existing papers, it's been applied for patient selection, education, adverse event prediction, operative planning, operative execution, and robotics. Ties in nicely to the course you guys will have coming up tomorrow. Image analysis, image guidance, hardware identification, and even resident and fellow training. But despite all of this, and despite how popular artificial intelligence is, there's actually no firm definition for AI. Very broadly speaking, it's just intelligence of mechanical or non-biological origin. And this involves some factors, things like problem solving and critical thinking, planning and anticipation, learning and abstraction, as well as some element of self-awareness when you're talking about general artificial intelligence. And kind of the two subsets of AI are weak AI, which is what we'll be discussing today. These are very specialized algorithms for specific problems. And then kind of the more science fiction, but perhaps not for too much longer, strong or general AI, which is broadly applicable artificial intelligence. Within the subset of AI, another important term is machine learning, which is just the use of algorithms to enable computers or other mechanical systems to adapt and develop inferences from existing data. And then a further subset of machine learning, which I think at least one of our presenters will discuss, is deep learning, and that's the use of a special architecture that's actually modeled after the human brain to enable even better learning, in computer and mechanical systems. And then finally, there's this concept of a large language model, which is an algorithm that's informed by and interacts with human language, and and typically on a massive scale. And these are the chatbots, ChatGPT, that are becoming more and more popular with time. And finally, I went straight to the source. I asked ChatGPT to define artificial intelligence for us, but I know the audience is mostly spine surgeons, so I made it appropriate, at a 6th grade reading level. And this is what it provided. Artificial intelligence, or AI, is when computers or machines are designed to think and learn like humans. They can recognize faces, understand speech, play games, and even drive cars. AI uses special programs and lots of data to make smart decisions and solve problems, just like our brains do. And with that, I'll turn it over to our team. We've got Tom No, our spine fellow, JD Patterson, PGY5 from our residency program, Audrey Demand, PGY4, and Ryan Farrell, PGY3.
All right, let me see if I can share my screen here.
just sure it's on the appropriate slide. And just want to confirm everybody can see that.
Just put it
Great.
into there. Perfect.
Great. Okay. So my name is Tom No, and I'll be presenting today on a paper called the Machine Learning Approach for Predictive Models of Adverse Events Following Spine Surgery. So just as an overview, I'll be introducing a concept in terms of how we look at these different types of studies, a checklist of sorts, a model that I actually really like using for reviewing papers, something I learned actually back in my training from Beverly Walters. And then obviously reviewing the paper and then leaving a little bit of time at the end for some questions. So I'll jump right into it. CASP is essentially a critical appraisal checklist program. It was a program developed back in the 1980s, born out of the UK, and was essentially the grounds for this was this idea of raising awareness across sort of like a rising tide across all of medicine. The problem, I think, at the time was that there were a bunch of different papers with a bunch of different statistical analyses, and there wasn't really a cohesive movement in terms of trying to analyze these papers. So if you ever do get a chance, I think it's a phenomenal website. They give you a checklist for everything from randomized controlled trials all the way to cohort studies such as this. So if you do get a chance to peruse that site, it could be very helpful, I think, not just in journal clubbing, but then also in, obviously your day-to-day interactions and digestion of different evidence-based medicine. So to jump into it, this is just going through their checklist. Did the study address a clearly focused issue? I thought it did. The study aimed to predict, obviously, adverse events following spine surgery, in this case, using machine learning models. It used a larger database than what was previously sort of known in literature. I think the biggest study before this was a study by Bakalis, and that was using, I think it was Medicare data, but they had something around 300,000 patients, whereas this one, was well above 1 million. Was the cohort recruited in an acceptable way? Yes, I thought so. The cohort included patients, obviously, like we just said, from a combination of market scan and CMS data. And I thought it represented a pretty diverse population, especially when you're looking at those two types of databases. And so for us and for the utilization within our clinical practices, I think is very generalizable. Was the exposure accurately measured to minimize bias? I thought so. Included, all the demographics and comorbidities. They had a relatively long list of all those different things, and they were measured using standardized coding. Now, the one potential pitfall here is that there are coding errors because a lot of that is left up to our coding specialists, oftentimes in most settings. Was the outcome accurately measured to minimize bias? I wasn't really sure, but probably yes. I thought that the adverse events, because they were defined using ICD-9, it's a little less relevant because there have been some changes over time with the ICD-10. Just one of those, just kind of using lumbar disc herniations as an example. The ICD-10 has sort of increased the specificity of those types of diagnosis codes. So you might have a lumbar disc that's caudally migrated or herniated or so on and so forth. So those things are going to be missed because they were using ICD-9 codes. So have all the authors basically eliminated the confounding factors, and have they taken account any of the confounding factors in the design and or analysis? So for the first question, I said maybe. The Medicaid status, preoperative infections, comorbidities were all included, and they have a relatively long list. But if you go through their supplemental S7 page, there are lots of things that they didn't include or couldn't include because this was a database review. But things like institutional rates, dural tears, et cetera, things that are maybe more nuanced to us as surgeons. And then for B, I thought, yes, I mean, they used two different types of regression analyses, and that was previously done in other papers. So I'm not a statistical analysis expert, but I thought it seemed reasonable. Was the follow-up of subjects complete enough and long enough? I thought yes, a 30-day post-op period seemed fairly standard in terms of capturing some of those early complications. You know, in terms of long-term results, it's hard to know. I think typically, we like to follow patients out to almost 2 years if we're looking for some of our longer-term complications. And then, of course, the global period is typically another metric that's used, which is 90 days. So those are obviously missed. What are the results of the study? So the model essentially, I thought, achieved kind of a modest accuracy, 0.7 to 0.6, and I'll go over that in just a second. With pulmonary complications being the most predictable, and then of course Medicaid status was a significant predictor. How precise are the results? So they gave their confidence intervals and p-values. For example, CHF and pneumonia was just one of the things that they listed. They have all of them for your review if you're interested in looking at a specific complication. But going back to sort of the idea of what would we consider a good AUC, this is kind of just across industry standards. I mean, if you're looking for something like a cancer detecting type of diagnostic test, of course you want the area under the curve to be outstanding. And so what's a good area under the curve in terms of looking at prognostic factors? That's a little bit more up to your personal interpretation, but generally across, I'd say the industry of statistics, it seems that a 0.7 to 0.8 is acceptable. And again, if you're looking at the results of this study, the best case scenario in terms of pulmonary complications, if you're looking at, what is sort of the best or the most outstanding number was 0.76, and so that falls essentially anywhere between poor and excellent. So do I believe the results? Yes, I thought so. I mean, it aligns essentially with what we know from previous research. Medicaid status, for example, was something that had been looked at previously and was the first thing to kind of pop up. But again, this is relying very heavily on administrative data, and again, going back to the moderate area under the curve. Can the results be applied to the local population? I thought so. It's a very large data set. It includes a very diverse population, but of course, there may be local differences at your hospital, in your state, and so that may limit some of the applicability of the study. Did the results of this study fit with other available evidence? Yes, I thought so. Just like we previously mentioned, using Medicaid status, they potentially could have included maybe a few other studies, just citing some of the other measures, like the pulmonary complications and CHF and stuff like that. But I think if you did your own digging, you could probably find those. And then what are the implications of the study in regards to our practice? I thought it was interesting because it kind of helps us in some ways to provide risk stratification, and then to potentially actually create interventions to reduce, based on a case-by-case basis with patients. And I think what's the biggest sort of learning piece from this is that, machine learning is an incredibly powerful tool, and it can help us to analyze a lot of these other relevant data sets that we might be interested in. For example, you could throw in the variable of endoscopic awake surgery and kind of see what those results are compared to some of the other variables. So I think that's the end of my slides, and I'll take any questions.
Yeah, Tom, that's a great presentation. One of the issues that's raised frequently with respect to all of these kind of narrow AI applications is the issue of data overload. And every time we log into our EMRs, we see every time there's a new little indicator, some risk prediction or something like that. You've been doing this for a while now. What would be your threshold for actually using this?
Yeah, that's a great question. I mean, for me, I think one of the things I think that's really helpful from this is that it can give us information in a way that allows us to see some of our blind spots. I was thinking about some of the time I spent in Boston, and there was this amazing study where they put in a bunch of MRI scans into a deep learning model. And they said, okay, well, tell us how you predict for a GBM, for example. And it spit back this weird algorithm that said, well, if you take a T2 and a FLAIR image and you look at the difference between the two, it helps you to diagnose the IDH mutation, for example. And we were like, what? That's crazy. Like, how do you figure out the IDH mutation of a GBM with incredible sensitivity and specificity based off of these scans? And it's only because the machine was able to help them predict that. And I think those are, the types of findings that, will help us to kind of not find these things serendipitously, but actually go through a robust analysis over and over again to help us sort of leverage the data that we're gathering every single day to improve our own clinical practices. The pitfall here, obviously, is that, if people become too administratively reliant on these things, people may start inferring some of this into, bigger things like our reimbursements, for example, and things like that, which I think is why we need to kind of protect the data and then also leverage it in a way that's useful to improving our performance.
Yeah, that's a great perspective. I think you touched on a couple important things there. Many of these narrow AI applications often just end up kind of recapitulating things that we already know. But then sometimes you have these emergent properties like the one you mentioned where you compare the two imaging modalities and you would have never thought that would actually extract something useful, but it does. I think that's one of the main promises of AI in the future, that'll keep happening more and more often. Very cool. I think we have JD Patterson next.
Dr. Patterson, your microphone's muted.
There we go. Sorry about that. All right, so I'm JD. I'm one of the fifth-year residents at Methodist. So our paper is using machine learning and deep learning algorithms to predict postoperative outcomes following anterior cervical discectomy and fusion. This is out of Northwestern, did this study. Some of the background. So obviously, healthcare utilization is a big topic right now as far as, our cost of healthcare, and in particular, surgical patients can account for up to 20% of total hospital readmissions. And some recent data has showed that there's been a marked kind of hospital resource utilization after ACDF surgery, including readmissions and ER visits. Obviously, one of the concerns after anterior cervical surgery is, could there be a hematoma or something like that? So I think pretty much everybody has a pretty low threshold, if they get a call from a patient with concerns, to kind of send them to the ER. So AI, I think, is one area, within ACDF, that these predictive algorithms can kind of help us out in minimizing some of those concerns. And then machine learning has a distinct advantage over some of our conventional statistical modeling because it has the ability to accurately predict postoperative prognosis. So from this paper, a total of 1,026 cases were included. Patients were age 18 to 88, 10-year period, and included all the Northwestern hospital locations. Their primary outcomes they were looking at were 90-day readmissions, postoperative length of stay, and non-home discharge. And then their definition of extended postoperative length of stay was 2 or more days, which is what they defined. They looked at 4 different machine learning models and compared those: extreme gradient boosted trees, balanced random forest, elastinet, and deep learning neural network. They computed the importance scores of all these models and compared them. And then they looked at a total of 64 different predictors that included patient demographics, lab, surgical history, operative time, things like that. So this is just kind of a background kind of on what random forest is. This is kind of one of the more popular models and when looking at machine learning and these algorithms within healthcare. So what it is it's called the forest because you have these essentially like little decision trees that are all yes or no questions. So kind of in this instance, you have, if you ask it, what fruit is here, it may go through, well, is one of them red? Okay, yes. So is one of them, smaller than 5 inches? So yes, and you go down there and it decides apple. This one, it kind of decides wrongly. It sees the yellow maybe, and then kind of goes down the wrong thing, and I guess it's banana. But within a random forest, it performs something called majority voting. So it's going to perform the same kind of decision tree multiple times, and then it'll go with the correct answer of the majority. So it'll just exclude that, wrong answer of banana. And that's how it kind of learns. This is really similar, if anybody remembers a game that's been around forever called 20 Questions, where this little game is really simple, but it kind of guesses what you're thinking. So you'll think of a word and you go through these series of yes, no questions. And in the end, it normally, and it's pretty accurate, kind of predicts what word you were thinking of through these kind of yes, no questions. And then just another important term, and Tom kind of talked about this, is the area under the curve for all of these models is important. And like he kind of talked about, 0.5 is essentially a 50-50 if the algorithm is correct at predicting it. So that's like a coin flip. So that's not very good. But then the closer to 1 you get, that means it's the closer to that the model is 100% accurately predicting. So as far as the results of this paper, these are just some of the demographics and spread. And then this is the performance of all the different machine learning models they used here. So for the benchmark, we see their area under the curve was 0.5. So that was not a good model really at all. But then the balanced random forest here had a pretty good area under the curve, as well as the XG boost, at least for non-home discharge. The 90-day readmission wasn't too predictive there, but and this is kind of goes along with what we see in a lot of these type of studies, is the balanced random forest is kind of a really good model for this type of as far as predicting kind of post-operative outcomes and things like that. So for their results, this is A here. This is for the extended postoperative length of stay. Again, that was what they defined as greater than length of stay greater than or equal to or greater than 2 days. Then for that one, BMI, pulmonary conditions, and ASA class greater than 2 were some of the most important characteristics there. For non-home discharges, age was actually the most sort of important factor there, as well as, again, pulmonary conditions, ASA class greater than 2. And then for the 90-day readmissions, we see the age and BMI is less important. So they just are only showing 12 of these different factors in these graphs, but again, they had 64 total different factors that they were considering. And that's good with these models because what that means is there was 64 different seeds is what they kind of are termed when you're using a balanced random forest. And so the more of those seeds that you put into these algorithms, the more accurate your results will be, because it gives the algorithm and the program kind of more options and more decision to go through these decision trees and then more accurately kind of predict that. So there have been, I think there was another paper within the last couple of years that looked at ACDFs as well, but their area under the curve wasn't quite as good as this paper, because they had much lower kind of a seed number there. So in this study, BMI was a highly weighted feature for both extended length of stay and non-home discharge. There has been another meta-analysis that found that BMI was significantly associated with longer hospital stay and increased operative time. And then some other smaller studies have also showed that maybe BMI doesn't have as much of a difference. But it does seem to, the results of this does seem to align with kind of other studies we've seen. Age, this is another top covariant across all the outcome models, and especially for the non-home discharge. There have been some studies that say, maybe age isn't as big of a risk factor, and doesn't have much significant effect, but that's sort of what we saw in this model. And like I said, this includes over 1,000 patients. So the more these models can include patients, have more of these kind of seeds and everything, the more accurate and predictive they can get. So kind of the benefits of this machine learning, like I said, it can incorporate many different factors that would just be too time consuming for a human to sit down and individually analyze each one of these factors through sort of standard statistics. And it's actually even easier and better the more of these factors you have in these models for the models to actually learn them. There are always limitations, though, potential errors in data abstraction, cohort exclusion. One of the reasons the balanced random forest can be good is it does help eliminate a little bit of these limitations. One of the limitations can be something called overfitting, where essentially if the algorithm kind of makes a wrong prediction, with overfitting, if you have an algorithm that isn't doing like the majority voting, like in the balanced random forest, the algorithm can sometimes kind of go down the wrong pathway and follow that wrong prediction. Whereas since in the balanced random forest, you have this majority voting application there, that you kind of eliminate that overfitting. And then, of course, the more complex these statistical models and everything get, the more difficult it is to sort of, for us to self-check that there's not errors there. But I think we're kind of in a pivotal time right now with these kind of papers where, kind of what we were talking about with the last one is, with these machine learning papers and, outcome predictors, we're not at the point, just right now where we're saying these are 100% solid gold, we're going to change our practice based off of these, but we're at the point where we're comparing them to what we know before and kind of building our trust in them. So big future out there, obviously, for these. The more data we get, the more accurate it'll be. This is being used across all of healthcare. I know that there's a kind of widely used now sepsis model that works off this kind of these AI algorithms that Epic has included, that basically kind of scans all the patients' kind of demographics, and is being widely accepted now. So I think we're going to start seeing more applications like that, sort of widely brought out.
JD, did they give any sense of the quality of data they were using? Like, how did they screen the data input?
Yeah, so all of their, as far as selection, that went all off of CPT codes, but they did individually go in and manually look through all the cases and make sure that the CPT codes were billed correctly to the correct surgery. They went through and looked at all the op notes. They also went through and they took all their CPT codes for posterior cervical fusions as well, and just went through all those cases and made sure that they weren't wrongly billed, that to make sure that there wasn't actually the anterior cervical cases were incorrectly in the posterior cervical group. And then if they were, then they could have crossed those over to the other group.
Yeah, I think that's one of the main limitations with these kinds of studies. You mentioned they were looking at 64 different data factors for each patient. One of the issues is this idea of garbage in, garbage out. we've all been there, right? You're just trying to finish a note, you check some boxes, history of COPD or whatever. And a lot of the time that might not be 100% accurate. So if the algorithms they're working aren't operating on accurate data, it impacts the quality. And there's no way an algorithm or a machine learning program will address that. There are other issues to be addressed to increase the accuracy of these things. I think Dr. Chapman has a question.
Yeah, I love this study. I love the topic again, and you have a great team there. So my question to you, JD, is who benefits from this kind of an application? Is this the patient? Are these us, the surgeons? Is this the hospital system or the insurance carriers? I know this goes into a sensitive area, but as I see this applied in this particular case, I'm in my 60s now, but I find myself in pretty good shape. Not as good as Dr. Freyvert, but I don't want to be denied care if because I fall into an age algorithm. So who benefits from an application of this? Is this something that more the administrative side will actually then use for denial of care?
I mean, that's the problem, with these is that if insurance companies, have access to these data, I know that there's a big, controversy going around right now with that insurance company that was trying to, basically say that they would only, they wouldn't cover anesthesia time for what they predicted the case could be. So there's a lot of controversy with that going around. So that is there. I think as surgeons and hospitals will benefit a lot from this. We can, but you always have to take into account, your patient population in your region as well. And I think that's one area that AI will eventually kind of shine, is that your country region and even your sub-region in that country may have a very different patient population. So that's the problem with, even these non-machine learning papers that we have, is that, if it's a nationwide thing, you may get different results from a single institution. Is that because, the data is really wrong, or is that because populations are very different? Whereas these AI models, you can very easily change them to look at, okay, nationwide or just at your local thing. So, for Texas, BMI for us may be way more important in predicting some of these. Whereas in New York, BMI may not be an important predictor of, predicting readmission. So I think that's sort of a potential area that it'll help us out as surgeons.
Very good. I think we have Audrey next.
Can you see my screen?
Yes.
Awesome. I'm Audrey Deman. I'm one of the PGY4s here. Thank you so much for having us back. I'm excited to talk about this topic. I know it's really hot in the literature right now. I'm going to go over an article that came out of Korea called the Deep Learning Application in Spinal Implant Identification. So I know we've sort of already touched on this through Dr. Freyvert's discussion, but what really is machine learning? And to me, this is all quite new, but it is a subset of artificial intelligence software. And then deep learning specifically defines multiple layers of artificial neural networks. That's kind of what Dr. Freyvert described as this was created based off of the way our brain processes visual information, starting from a very simple, yes or no, black or white, and then redefining into more detailed features, kind of like shapes, designs, and how how that looks in subsequent layers. So this study, it was designed as a retrospective observational study looking at two different hospitals. They had 2,894 radiographs looking at specifically only single segment lumbar surgery. And then those 2,080 radiographs were defined into only AP or only lateral. And so they subdivided that into 5 different implant companies. We have Biomed, CG Bio, Medtronic, DePuy-Synthes, and then Stryker. And with those different implants, they analyze the data with 3 different types of deep learning networks and deep learning algorithms. This is just to show that they have an equal amount in each company, and then each subset of AP and lateral radiographs. No discrepancy there. It's almost perfect. So what deep learning algorithms did they use? The first one that they compared was Google Auto Machine Learning, and that is a platform that's available for public use. It uses cloud auto machine learning, this vision subset that is a imaging classification model that they modified, but it's sort of already made for them. And then Apple Crete also has a machine learning model, and that allowed them to have a direct comparison with performance of standard deep neural networks and using a different transfer learning algorithm. Then those 2 were, publicly available, and then they created their own doing standard deep neural network with this company called PyTorch. And so that's kind of the figure I have off to the left, which makes creating an algorithm sound very simple. I'm sure it's not quite so simple when you sit down to make it, but you start with your data, and then you can either use a predefined model or build your own to suit the specific question that you're asking. And as you file that data into your model, making modifications and evaluating if it's really detecting what you want it to. And then as all of this AI you have to improve that through experimentation and improve. A lot of the time they have 70% that's just to prove that the model works, and then they compare that to 30% of their other database. This is some of the results that they had comparing their conventional transfer learning model that they made versus the Apple and the Google different machine learning models. Looking at the precision and the recall of pedicle screw identification, you can see that this is extremely high accuracy for something that is so quick. And there is a small decrease in the ability for apples to identify it, but compared to the model that they made, 98% accuracy. I think it's pretty incredible as far as identifying those pedicle screws. And then this is sort of a busy slide and a table, but they talk about what a confusion matrix is. And a confusion matrix is essentially just everything we learned in basic statistics, which is detecting is this true positive or not. And so they implemented if what the screw actually was versus comparing how many times the algorithm predicted that would be positive. It was actually for example, actually a Stryker screw or not. And if you look at the areas that are highlighted, we're dealing with 100%, 95, 97. So it's really doing an excellent job at identifying the pedicle screw. The one on the right is comparing just the conventional transfer learning model that they created. And I think the only one that they didn't do quite as good of a job at, which you can see, is Zia. And just the left is the Google auto machine learning model. So the Apple one, they didn't have that available, and then I just want to go into a little bit of discussion. So we've proven in this study, they showed, okay, I have a data set of 1,400 different radiographs, and they did almost 97% accuracy at identifying right off the bat what that screw was. So I think that that's useful. A lot of the time we do surgery and the patient's either not an epic or you have a different EMR and you don't know, the patient doesn't know what company their screws are. They don't know when their surgery was. And then you're stuck having to do some sort of revision disaster. So having an AI tool that was able to identify that for you, I think would be extremely helpful. And to that point, you're able to identify the implant much faster, as opposed to, you take a picture of it, you send it to your rep, and they say, oh, I don't know what this is, and then they send it to somebody else, and you're spending a lot of your valuable time trying to identify how to prepare for that kind of case. And then obviously it's low cost. I mean, if you have an algorithm that works and you can just implement it very quickly, that would be useful. And another thing, which I think is just the gold star, is a high accuracy. So, of course, everything has limitations. This study specifically only looked at 5 different companies. So to really say, I want to implement this in my practice, you'd have to expand it to include all the other major distributors. And some of our reps, I don't know about you guys in Seattle, use a similar software called What's It. It's an app that they can implement patient de-identified x-rays, and it's supposed to identify what type of screw that they have. The other part is that this only specifically looked at lumbar pedicle screws in single level surgery. So how does this machine learning apply to other types of screws, longer constructs, maybe mixed constructs? And the last part is it's not commercially available. So they proved it in a study, but they don't have a plan for how to show that we can use this out in practice. Some future directions is sort of leaning on that. Limitation is expanding it to additional companies, proving in another deep learning network that you can accurately identify pedicle screws, and then identifying the same type of learning model that could work in thoracic cases, cervical cases. I don't see why they couldn't further that, expand that to do deep learning algorithms that maybe identify interbodies, patients that had cervical fusion 20 years ago, or what have you, just to give the surgeon good information about what kind of revision they're going into. And then just making this commercially available through an accessible platform. And I think that would have to wait until they'd expanded it to all of the different companies, and then we could actually look at cervical, thoracic, and lumbar, and use all of that data to sort of plan for your future surgeries. So with that, I'll take any questions.
Yeah, Adri, that's fantastic.
You guys have.
It's a very controlled set of circumstances demonstrating this. You've seen the actual commercial product in use. What do you think? We've had some cases together.
Sure, we certainly have. I think there's a large room for improvement in what is commercially available. For example, you go into a revision case, and even if they say, oh, I know what this is, you have your revision set open. I don't know in y'all's experience, but what I've seen is they hand you a hex, it doesn't fit, this one's too small, this one's too big, and just kind of a large waste of your time. Dr. Freyvert and I, we opened a revision set. We had what we thought was available, and absolutely nothing fit. And we spent over an hour doing like 20 different screws. We had to helicopter out. So for that, that's more anesthesia time for the patient. It's obviously more frustrating for the surgeon. And if you could have just gone into that case, known exactly what you needed, and had that tool available, I think that could optimize your practice.
Yeah, absolutely. Don't get me wrong, I like the tungsten carbide bit a whole lot, but I don't like it that much. I think Dr. Chapman has a question.
One question I've in these kind of exercise. Thank you, Audrey, for a nice presentation. That is, where did this model fail? So did the authors provide an analysis of what went sour when their system could not identify hardware correctly? I like to learn from failures. I don't like to have failures, but I just think this is a statistically very relevant proposal.
Yeah, I think that's an excellent point. And all they focus on all these positives. Oh, we're identifying 97% of screws, but they, from what I read, didn't really delve into what in the learning module failed that made them inaccurate, or tested it is false positive. that's certainly a weakness that I think they need to iron out in the further studies.
Thank you.
Very good. All right, Ryan. Oh, Tom's got a question.
Oh, sorry, Audrey, just had a quick question. Do you know if they were using actual DICOM data or were they using just like pictures? I don't know if you
Pictures.
know. Just pictures? Oh, okay, that's great. I mean, DICOM data certainly includes more information, and there are different ways of digesting that information too. But yeah, if they're just using pictures, then obviously it could be one step closer to like an iPhone app or something like that, which I know has been done. I think that there was a recent article with Jun Kim at Sinai. I do some work in this, that's why. So I was kind of curious.
Sure.
Very cool. All right, Ryan, bring us home.
All right. Hi, I'm Ryan. I'm one of the third-year residents. And get this shared. Okay. I don't know if it's letting me share yet. Let's see. There we go. Okay. So my paper was the predictive model for selecting the UIV using a machine learning approach, and briefly just the authors of the paper. So the goal of the study was to train and validate an algorithm that could actually just mimic the surgical of two surgeons at their institution, and in regards to how they would select the UIV based on certain objective parameters, and they kind of separated it basically between upper thoracic and lower thoracic, like T1 to 6 and T7 to 12, and they included multiple kind of specific patient factors. Let's see. And so kind of the benefits of having an artificial kind of intelligence tool is being able to just synthesize very large volumes of data that you can then kind of just tailor to the specific patient. And I thought it was interesting. The goal wasn't to say what's how can we predict what is the best UIV, but to really just can we create this algorithm to accurately predict what these two surgeons would predict based off theoretical objective parameters. So, and it was a retrospective review, single center, and it was just adult-only patients with ASD who underwent fusion above L1, and they defined spinal deformity as coronal Cobb angle greater than 20 degrees, SVA greater than 5, pelvic tilt greater than 25, and PIL mismatch greater than 10. Pretty standard parameters. And they excluded, any other degenerative, idiopathic, or iatrogenic, so like congenital or traumatic or neuromuscular scoliosis patients were excluded. And in terms of their sagittal alignment parameters, also pretty standard measurements with pelvic incidence, pelvic tilt, lumbar lordosis, PIL mismatch, T10, L2, thoracolumbar kyphosis, SVA, and the T1 pelvic angle. And they they measured the preoperative baseline, and then at 1 year post-op for all their patients, and also recorded rates of PJK, PJF, instrument failure, pseudoarthrosis, and the patients that needed revision surgery. And they briefly described their neural network model as having just 3 main layers: as a input layer, a hidden layer, and an output layer. And for their other different parameters, they also had coronal parameters, and nothing really too out of the ordinary, and kind of how they created what set of parameters they wanted to include. And they also had a goal PIL mismatch, so each patient they had a goal in mind for that. And then so they wanted to train the algorithm first, and then they had a validation group as well to test the accuracy, and included 2 patient examples. So they include the age, their preoperative measurements, and then kind of the alignment target for the surgery. And then the algorithm would suggest based off those what these 2 surgeons would choose for the UIV, whether lower or upper thoracic. And they did paired t-test analysis for their preoperative and postoperative radiographic parameters, and they had their patients divided into 3 cohorts. The majority were for just the training the model, and then 15% for validation and 15% for testing. And they also did the ROC curve analysis. And so they had a pretty good number of patients at 143. Most were female and middle-aged, and BMI was about average, and only 35% of the patients were in the upper thoracic group. And they also included in their analysis just various operative details of the surgeries, and also the preoperative and postoperative alignment measurements. Let's see. And they also kind of recorded the quality of life parameters at preoperative and postoperative, kind of through just standard validated mix. And also they did a pretty thorough analysis of all their preoperative and postoperative alignments, and in terms of looking at just overall their upper thoracic and lower thoracic groups. There was a significantly larger thoracic kyphosis for the upper thoracic group, as well as a larger residual Cobb angle, but there wasn't really any statistical significance for the other parameters between those 2 groups. And they had pretty standard rates of postoperative revision, pseudoarthrosis, PJF, and PJK. And so 101 were for training, 21 for validation, and 21 for testing. And that's interesting. They had a pretty good accuracy for their testing cohort at 81%. So 4 out of 5 times the algorithm would accurately predict what the surgeons would choose. And the overall area under the curve for the testing cohort was was acceptable at 0.829. So it seemed to have some good predictive power. And so it was interesting that it was just to kind of mimic 2 surgeons and how they would choose the UIV. It'd be kind of interesting to think, as they get more data and included more surgeons, how the accuracy might change, if it would get better or worse, or how it would vary from institutions, and kind of how different thought processes at various places are. And I think it would be kind of an interesting tool just to kind of look at how different programs kind of choose their UIV and their philosophies behind it, just quickly go through it all and not just have to spend hours and hours digging through individual data. And in terms of why their accuracy theoretically it wasn't 100%, there's a lot of non-objective measurements that go into selecting what you would choose for UIV, like patient health, patient expectations, various factors that you can't really easily put into an algorithm. And then also just the very large heterogeneity among the spinal deformity patients. So overall, in that context, I thought 81% was pretty reasonable. And the authors did drive home, the obvious, ambiguity in terms of, what is the optimal UIV. So this does seem like it would be, a helpful tool, especially in the sense if maybe you're on the fence on whether, what level to choose, like you really aren't sure. This might just be something kind of in your back pocket to see, what this, algorithm might say, especially as, if they build upon it and expand its scope, just to kind of give yourself a check and see, hey, is my thought process kind of more in line with what most people think or not? So I think that would be, the most useful aspect for it. And in terms of their specific, algorithm they chose, they did seem to, show that their algorithm, does have benefits, over just various, logarithm regressions. And they also showed, another, artificial neural networks that looked at, other aspects of spine surgery. They also have shown to be, rather accurate and offer some power there. So I've been looking at how, complex this, just this simple decision can be, but, with all the different factors, this could really help streamline the rather complex decision-making process, especially, when you're busy and having a lot going on. And so for the limitations for the study, I mean, a good number of patients, but, it just would be really exciting to see, how the algorithm develops with more data and more surgeons. And so otherwise, I think it just might be something that helps add some clarity or something objective to, a pretty difficult topic and contentious topic in spine surgery. And otherwise, any questions?
Yeah, Ryan, this is fascinating. I think of all the papers presented, this one is probably the furthest from. I think you may need to stop your screen sharing. I think this one is furthest from practical applications at this point. But in a way, you're an aspiring spine surgeon. You're not that far from being in practice. Do you think it's going to impact your training to have a computer program where you can just plug in some data and ask it, what would Jens Chapman do? Are there any implications for trainees with this kind of technology?
All right, definitely. I think so. I mean, especially when you're kind of coming through training and more unsure. I mean, I definitely would defer to what more expert opinions would be over my own. So it'd be tempting to just go with whatever that tells me because I just would trust their opinion more than my own. And then also it'd be interesting to see why they chose it and why I chose something else. So just to kind of put it in my face, why my thought process is different than others. So I think it would be really interesting just to see how other people, think about it.
Go ahead, Jens. Did you have one?
Yeah. Hey, so sorry to hog the questions, Ryan. I really like this article, and we all know some of the surgeons involved. And the variable that I did not see addressed there was, did they actually have soft landing fixations in there as a variable or not? Because again, several of those surgeons sometimes use it and sometimes don't. So banding, hooks, cables, stuff like that to create a soft transition zone, was that addressed as a variable?
I don't think they did mention that in the paper, but that's a point.
Yeah.
Yeah, I just want to bring up that I thought that this was very interesting study as well, and thank you for the presentation. But obviously, some of the more challenging decisions would be the kind of granularity of not just upper versus lower UIV, but do you need to put in stopping at T10, T8, T9? I think it would be really interesting, obviously to see a more kind of iterative process, which I do think may be more applicable in some of our decision making and give you a little bit more information. But I thought it was a very, very interesting study.
Let me wrap things up here. I'll just show last two slides. So we touched on quite a few things that are relevant in terms of limitations to all of these studies. One thing I'm going to emphasize again, and this comes up frequently as a criticism for AI, is data overload. This is an AI generated picture of what AI thinks data overload looks like, and these studies were just a small snippet of everything that's out there, and there's so much more work going on. I think inevitably at some point in the future, all of this will be consolidated and we'll have a truly useful data output. But I think we're at least a few years away, if not longer, from true practical application of all of these developments. And then the final thing, and this was a little bit less emphasized because most of these studies are narrow AI, but AI hallucination is a well-known phenomenon where some of these kind of authoritative algorithms will sometimes give results that are actually much less based in reality than you would hope they would be, certainly in a field like spine surgery. As a case in point, this is Jens Chapman, and I asked some AI to draw Dr. Jens Chapman holding a scalpel standing in a field, and it protested a little bit, but eventually I got this, and this, and I think we still have some work to go. And with that, unless there are any other questions, we'll wrap up.
Thank you, guys. This is a great journal club, and we really appreciate all the input from the group and all the great presentations. Thank you.
Thanks. Take care.
Bye-bye.